We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Hello friends, now let us begin the concept of inverse Laplace transform. So let us first define inverse Laplace transform. So it is a easy concept and we should be able to solve so many very good examples of it. So the definition is like this: if Laplace transformation of f of t equal to f of s, then f of t is called the inverse Laplace transform of fs. So it is denoted like this: inverse Laplace transform of fs equal to f of t. So this is the way. So now it is like this: if f of t is there, if we apply Laplace transform, we get f of s, and for f of s, if we apply the inverse Laplace transform, we get f of t. But then the natural question arises, is it possible to get the inverse Laplace transform of every function? Okay, so, and is it unique also? So that is also the question. Okay, because we know the inverse image may not be unique also. So the natural question is, that the inverse Laplace transform for all function exist, that means existence, and another is uniqueness. Okay, so there is one condition where if that condition satisfied, then the function is having the inverse Laplace transform. Basically inverse means the existence of inverse function, and we know even in trigonometry also the inverse function exists in a restricted domain. Okay, so inverse Laplace transform exists under certain condition. So first, so fs is the Laplace transform of f of t. So if these two conditions satisfied, like limit s tends to infinite, fs is 0, and second condition is limit s tends to infinite, s into fs is finite. Okay, then we can have the existence of the inverse Laplace transform, and the uniqueness may not be there, but in most of our practical purposes we assume that the uniqueness is there. Okay, so that is we assume. Okay, so the Laplace transform exists and it is unique also. Okay, let us list out some of the inverse Laplace transform formula. Okay, so see, we know the Laplace transformation of 1 is 1 by s. So the inverse Laplace transformation of 1 by s is 1. Then we know the Laplace transformation of, say, t power n is equal to gamma n plus 1 over s power n plus 1, and if n is integer, positive integer, then we write n factorial upon s power n plus 1. So here now inverse Laplace transform of 1 upon s power n plus 1. So inverse Laplace transform of 1 upon s power n plus 1 is equal to inverse Laplace transform of this. So this function is now on this side. Okay, so that is equal to t to the power n upon gamma n plus 1, or if n is positive integer, we write t to the power n upon n factorial. See, we know Laplace transform of e power at, and that is equal to 1 upon s minus a. So inverse Laplace transform of 1 upon s minus a equal to e power at. Then we know the Laplace transformation of sin at is equal to a upon s square plus a square. So inverse Laplace transform of, now we take 1 upon s square plus a square, a can be taken here, which is a constant. Okay, so inverse Laplace transform of 1 upon s square plus a square is equal to 1 upon a sin at. Then Laplace transformation of cosine at is equal to s upon s square plus a square. So inverse Laplace transform of s upon s square plus a square. See, you cannot take s on this side, only constant can be taken. Okay, s is a variable here. So inverse Laplace transform of s upon s square plus a square is cosine at. So you need to take care about the result, like 1 upon s square plus a square divided by a when you take the inverse Laplace transform. When inverse Laplace transform of s upon s square plus a square, you don't divide anything. Okay, then we know Laplace transformation of sine hyperbolic at is equal to a upon s square minus a square. So inverse Laplace transformation of 1 upon s square minus a square equal to 1 upon a sine hyperbolic at. We know in Laplace transformation of cosine hyperbolic at, and that is equal to s upon s square minus a square. So inverse Laplace transform of s upon s square minus a square is equal to cosine hyperbolic at. So these are the inverse Laplace transform formula. Then the linearity is also there. So it is like this: if inverse Laplace transform of f of s equal to f of t, and inverse Laplace transform of g of s equal to g of t, then inverse Laplace transform of a times fs plus b times gs equal to a f of t, that means a inverse Laplace transform of fs, and that is f of t, plus b inverse Laplace transform of g of s, and that is g of t. Okay, or you can have a inverse Laplace transform of fs plus b inverse Laplace transform of gs. So this is linearity, and we take the first shifting theorem for inverse Laplace transform. So first shifting theorem for inverse Laplace transform. Okay, so first shifting theorem for inverse Laplace transform. So its theorem is simple, very easy. See, what is first shifting theorem for our Laplace transform? So first shifting theorem for Laplace transform is if Laplace transform of f of t equal to fs, then Laplace transform of e power at f of t equal to f of s minus a. Okay, this is our first shifting theorem of Laplace transform. So the same thing we can do for the inverse. So what is the inverse? So inverse Laplace transform of f of s minus a equal to e power at ft, or you can say e power at inverse Laplace transform of fs. So this is our first shifting theorem, that inverse Laplace transform of f of s minus a is e power at inverse Laplace transform of fs. Okay, or if you have, say, suppose inverse Laplace transform of f of s plus a, then it is e power minus at inverse Laplace transform of fs. Okay, so now we can solve some example. So let us solve some example. Find the inverse Laplace transform of 3s plus 2 over s square minus 9. That means we want to find inverse Laplace transform of 3s plus 2 over s square minus 9. So this we can write as inverse Laplace transform of 3s over s square minus 9 plus inverse Laplace transform of 2 over s square minus 9. This we can write as 3, we can take it outside by linearity, inverse Laplace transform of s over s square plus 9 plus 2 inverse Laplace transform of 1 over s square plus minus 9. Now 3. Now what is the inverse Laplace transform of s over s square minus a square? So see, inverse Laplace transform of s over s square minus a square is cosine hyperbolic at, and inverse Laplace transform of 1 upon s square minus a square, so that is 1 upon a sine hyperbolic at. So these are the formula we can use. So which formula we can use here? Inverse Laplace transform of s over s square minus a square is cosine hyperbolic at, and inverse Laplace transform of 1 upon s square minus a square is 1 upon a sine hyperbolic at. So this formula we can use. So this is inverse Laplace transform of s over s square minus 9. So this 9 is 3 square, so a is 3. So that is cosine hyperbolic 3t plus 2, and inverse Laplace transform of s square minus a square. A square is 9, so a is 3. So that is 1 upon 3 sine hyperbolic 3t. So this is our answer. Okay, let us take one more example. Find inverse Laplace transform of 2 into s minus 3 square over s power 4. So now inverse Laplace transform of 2 s minus 3 square over s power 4. So first let us simplify. Inverse Laplace transform 2 can be taken even outside also, but let us see. This is s square minus 6s plus 9 over s power 4. So this is nothing but inverse Laplace transform of 2 s square upon s power 4. Separate out now. So upon s square minus 12 upon s cube plus 18 upon s power 4. So this is equal to 2 inverse Laplace transform of 1 upon s square minus 12 inverse Laplace transform of 1 upon s cube plus 18 inverse Laplace transform of 1 upon s power 4. Now what is inverse Laplace transform of formula? 1 upon s power n plus 1, and if n is integer, positive integer, then t power n upon n factorial. So inverse Laplace transform of 1 upon s power n plus 1 is equal to t power n upon n factorial if n is positive integer. Otherwise we write gamma n plus 1. Okay, so this is equal to 2. Now 1 over s square. So here n plus 1 is 2. So n is 1. So n is 1. So this is t only. 1 factorial is 1. Minus 12. Now this is s cube. So that is s power n plus 1. So n is 2 here. So n is 2 here. So that is a t square over 2 factorial is 2. Plus 18. This is s power 4. So n plus 1 4. So n is 3 here. So t power 3 over 3 factorial, and that is 6. So the answer is 2t minus 6t square plus 3t cube. That is the inverse Laplace transform of 2 over s minus 3 square over s power 4. Okay, let us take one more example. Find inverse Laplace transform of s plus 2 over s plus 2 square plus 4. So now we should know the first shifting theorem in inverse Laplace transform. So inverse Laplace transform of s plus 2 over s plus 2 square plus 4. Now what is the first shifting theorem? Inverse Laplace transform of f of s minus a equal to e power at inverse Laplace transform of fs. And here if it is f of s plus a, then it is e power minus at, an inverse Laplace transform of fs. So this is of the category here, this one, f of s plus a. See that. So what is that result? Result is e power minus at. So e power minus 2t, and inverse Laplace transform of f of s. So inverse Laplace transform of s upon s square plus 4. That is our f of s. Okay, this is f of s plus 2, and this is f of s, and here we use the first shifting theorem. So this is equal to e power minus 2t, and this is now standard. So inverse Laplace transform of s upon s square plus a square equal to cosine at. So this is nothing but cosine 2t. So that's the answer. Next, find the inverse Laplace transform of 1 upon s minus 1 square minus 4. So inverse Laplace transform of 1 upon s minus 1 square minus 4 equal to, now here we can use this result, first shifting theorem. Okay, so this is f of s minus a, and what is a here? 1. So here we write e power 1t t. So this is equal to e power t inverse Laplace transform of 1 upon s square minus 4, and this is standard result, 1 upon s square minus 4. So Laplace inverse Laplace transform of 1 upon s square minus a square equal to 1 upon a sine hyperbolic at. Now what is a here? 2. Here a square, and it is 4 here, so a is 2, so here we need to divide by 2. So this is 1 by 2 sine hyperbolic 2t. So that is the answer. You can write 1 by 2 e power t sine hyperbolic 2t. Okay, let us take one more example. Find the inverse Laplace transform of s upon s plus 1 square plus 9. Now this is not any shifting theorem or kind of things, because here not given s plus 1, okay, here only given s, so we need to take care and we need to do some work. So inverse Laplace transform of s upon s plus 1 square plus 9. Now what we can do? We can do like this. Inverse Laplace transform, here we plus add and multiply. So s plus 1 add and subtracts minus 1 upon s plus 1 square plus 9. And so we can do like this. We keep these two and separate out. So inverse Laplace transform of s plus 1 upon s plus 1 square plus say 3 square minus inverse Laplace transform of 1 upon s plus 1 square plus 3 square. Now first shifting theorem. So inverse Laplace transform of f of s plus a equal to e power minus at inverse Laplace transform of f of s. So this is equal to e power minus t inverse Laplace transform of s over s square s over s square plus 3 square minus, same way here, e power minus t inverse Laplace transform of 1 upon s square plus 3 square. Now inverse Laplace transform of s upon s square plus a square is cosine at. Inverse Laplace transform of 1 upon s square plus a square is 1 upon a sine at. So we use that result, e power minus t. Now this one is here s upon s square plus a square, so it is cosine 3t. Then minus e power minus t, this is 1 upon s square plus a square. So inverse Laplace transform 1 upon s square plus a square, so 1 upon a sine a t. So I need to write 1 upon 3 sine 3t. So that is our answer. Okay, take one more example. Find inverse Laplace transform of s plus 7 upon s square plus 8s plus 25. Now inverse Laplace transform of s plus 7 upon s square plus 8s plus 25 equal to, now see here, this denominator we can do like this, s square plus 8s. So can we write s plus 4 square? So this is s square plus 8s plus 16 and now plus 9. Okay, and here s plus 7, so that we can write as s plus 4 plus 3. So that's not difficult. So this is equal to inverse Laplace transform of s plus 4 upon s plus 4 square plus 3 square plus 3 times inverse Laplace transform of 1 upon s plus 4 square plus 3 square. Now what is the first shifting theorem for inverse Laplace transform? Inverse Laplace transform of f of s plus a equal to e power minus at inverse Laplace transform of fs. So this is equal to e power minus 4t inverse Laplace transform of s over s square plus 3 square plus 3 e power minus 4t inverse Laplace transform of 1 upon s square plus 3 square. And now this is very standard. So e power minus 4t cosine 3t plus 3 e power minus 4t, this is 1 upon 3 sine 3t. And so this is a e power minus 4t cosine 3t plus this 3 cancel, e power minus 4t sine 3t, or you can write e power minus 4t sine 3t plus cosine 3t. So that is the inverse Laplace transform of s plus 7 over s square plus 8s plus 25. It was asked in GTU summer 2017.